Thank you, Ian. I should say that this should be presented by my student, who is in Seattle, which is awfully close, but he couldn't cross the border because he doesn't have visa in time, which is unfortunate, but the good thing is he's already graduated, so he doesn't need this talk anymore for his job searching. He's got a good job, so he's pretty happy with that. So he left me here to present the work. So we're interested in a concept in computational geometry called medial axis. The definition is pretty simple. So if you have a shape, then the medial axis is made up of all the points inside the shape with two or more nearest points on the boundary. For example, this red dot has two nearest points on the boundary. This green dot has three nearest points on the boundary. So both points are on the medial axis. The definition works in arbitrary dimensions, which is nice and simple. The simple definition actually gives plenty of nice properties for a medial axis, which makes it a pretty good shape descriptor. So by definition, medial axis is centered, so it can be thought of as a kind of local symmetry axis. It is more compact than the shape in terms of dimensionality. So the medial axis of a 2D shape is a bunch of 1D curves. Medial axis of a 3D shape is a bunch of 2D surfaces. And it preserves all the topological features. So that includes connected components, holes, and topological handles. And last but not least, it can fully reconstruct the shape using the geometry of the medial axis and the distance from medial axis points to the boundary. So in this work, we are mostly interested in three-dimensional medial axis. So medial axis are three-dimensional shapes. So I'm going to go ahead and highlight a few applications that leverage these properties of medial axis. There are many applications that use the fact that medial axis is centered. So medial axis can be a good intermediate structure for creating volumetric meshes, creating three-dimensional roadmaps of environments for robot or camera navigation, and it has been recently used for creating interior support structure for 3D printing. The reconstruction property of medial axis can be used for simplifying the shape. You just simplify the medial axis, and that will simplify the shape as well. And a large sort of collection of algorithms take medial axis as input and produce even more compact skeletal descriptors like curved skeletons. And in turn, they have even more applications like shape decomposition, model retrieval, and even animation. Medial axis has found applications outside computer science. For example, in geology and material science, it was used to analyze the void structure, the empty structure inside rocks and minerals. So as useful as they are, medial axes are very hard to compute. There are algorithms that can take polyhedral shapes like meshes and compute the exact medial axis, but they have prohibitive computational cost. So they can only process up to a few hundred polygons. If you have much larger models, you need to approximate. Many approximation algorithms take as input a collection of voxels. Now, these voxels can be obtained directly from segmenting a 3D image, like MRI and CT scans, but they can also be converted from other mesh representations. So we've already seen a voxelization talk just now. So you can do that. Now, these methods, they're pretty straightforward. They usually work by stripping away layers of voxel at a time until you get to something in the middle. However, all these algorithms need to store and process all the voxels inside the shape. That means that they don't scale up really well as you increase the voxel resolution. And another sort of unsatisfying aspect is that theoretically they don't give you any guarantee on how well their results approximate the medial axis. Some other methods kind of taking a very different approach. They take as their input points on the surface on the boundary of the shape, and they usually derive their approximation from the Voronoi diagram of these point sets. Now, unlike the voxel-based methods, these methods use samples on the boundary, so they scale better as you increase the resolution of sampling. And also, most of them provide guarantees on their approximation quality, usually in terms of Hausdorff distance from the approximation to the medial axis. Now, these methods are really great. I think they represent the state of art of computing medial axis. One of the challenges which we found, which motivates this work, is that they often produce topological errors. So as I mentioned before, medial axis captures all the topological features, no more and no less. Many of these sampling-based methods do not provide any topological guarantee. And only a few do. But for the few that actually do provide guarantee, they are very complicated to implement, and they can be sensitive to numerical errors. So at the end of the day, their theoretical guarantees are often not delivered in practice. So here I compare the results of 3 sampling-based methods whose implementations are available. Now, these methods produce a visually similar results. However, their topology differ significantly. And to see this, I'm going to compute 2 topologic invariants, the number of connected components and the Euler number. The Euler number, if you're not familiar with it, is related to the number of connected components, the number of topological handles, and the number of voids. Ideally, if we have a good approximation of medial axis, it should have the same number of connected components and Euler number as the input shape. However, as you see here, that's hardly the case for any of the 3 methods. The first 2 methods generate tons of disconnected components, and another typical error which you don't see that easily are tiny void spaces inside the medial axis that are bounded by closed polyhedra. The last method by Amenta and Kaluri in 2001 is the only method that can give us something close. It produces a correct number of connected components, but however, there are still a few dozens of these little void spaces inside the medial axis. I would like to point out that the last method is one of the very few methods right now that can provide theoretical guarantees that their result will have the right topology if the sampling resolution is sufficiently high. However, in our experiments, as we tweak up the sampling resolution, these topologic errors don't really go away. So that tells us that it's really because of the implementation. Now, this particular algorithm is actually quite involved. There are multiple passes of Voronoi computation, and you need to compute geometric intersection, and all of which are quite sensitive to numerical errors. So I want to stress that it's actually quite important to have a medial axis with the right topology. For example, if you want to compute a curved skeleton from the medial axis, and if you have errors on the medial axis, then those errors will be inherited by the curved skeleton. Here is a concrete example. So I take the result of Menta-Kaluri, apply to the hand shape, and feed it into a curved skeleton algorithm. And you get a quite noisy curved skeleton. And we actually verified that every single one of those spurious branches existed to preserve one of those topological artifacts, whether it's a noisy handle or it's a little void spaces. In contrast, if we feed the same curved skeleton algorithm with a medial axis without topologic errors, you would get a much more meaningful skeleton back. And these branches of the skeleton will preserve the shape features rather than topological artifacts. And in fact, the picture in the middle is a result that of the method that I'm going to present today. So our method is another sampling-based method. It enjoys the benefits of existing sampling-based methods in terms of scalability, in terms of providing theoretical guarantees. And we actually provide guarantees on both how close our result is to the medial axis and the topological correctness. But what's most important, the method is simple and it is numerically stable. So we are better at delivering these theoretical promises in practice. In particular, now we can compute topologically correct medial axis as long as you have enough samples. So we'll talk about those sampling conditioning a little bit. All right, so what's different? The key difference between our method and existing sampling-based methods is that we don't take samples directly on the surface. We actually take samples that are slightly off the surface, but in a regular pattern. In particular, we voxelize the shape, just like the voxel-based approximation methods. And then we take the boundary vertices of the voxelization as our samples, and simply extract a subset of the Voronoi diagram of those samples. The most computationally intensive part of the algorithm are computing the voxelization and computing the Voronoi diagram of a bunch of points with integer coordinates. And both can be done very robustly using off-the-shelf software. The only remaining part of the algorithm is to extract a subset of the Voronoi diagram, and as I will explain later, it's a simple pruning process. So I think the key sort of the insight of this work is that by using these off-the-boundary and regular samples, you can get away with a simple and robust algorithm without losing much of the theoretical guarantees. I should also say that this algorithm bears a lot of similarity with the voxel-based approximation because they start with voxelization as well. The key difference is that we only use samples on the boundaries of the voxelization. That means our methods can scale much better when you increase the resolution of the grid. And also we provide theoretical guarantees on our approximation bounds, which voxel-based methods don't. So let's take a closer look at the algorithm. So given a shape whose medial axis we want to approximate, we define voxelization as a union of voxels whose centers are in the shape. You might also heard of the notion of Gauss digitization, and this is the same thing. So to approximate the medial axis of the original shape, we first start by looking at the medial axis of this voxel shape. It turns out that there is a really simple and accurate way of approximating the medial axis of this blocky shape. And what you do is take the Voronoi diagram of the boundary vertices and only keep the part that's inside the voxelization. And you can actually show that this subset, which we call the voxel core, preserves the topology of the voxelization and is very close to the medial axis, to the actual medial axis of the voxelization. In fact, I didn't show the error bounding here, but the distant bound is within the size of a single voxel. So now we have a nice way of approximating the medial axis of voxelization. Then you would hope that, okay, the same structure will just approximate the shape of medial axis of the original shape. But it's not that simple, because a shape and its voxelization can have very different medial axis. Take a very simple example of a circle whose medial axis is a dot. Its voxelization has medial axis that look like this. Even worse, the complexity of this green guy does not decrease as you increase the voxel resolution. It gets even more complex as you use finer and finer voxels. So what's going on here? Well, this is really because the medial axis is inherently sensitive to any boundary perturbation. And you can think about the voxelization as a kind of perturbed representation of the shape. So of course, you're going to have very different medial axis. Well, that's really bad news. So where do we go from here? Fortunately, a bunch of theoreticians in computational geometry community showed that there is a subset of the medial axis that's stable with respect to boundary perturbations. So what that means is, if you look at these two medial axes that are really different, there is a subset of each that are very close to each other. So our goal is to define a subset of our voxel core, which is a subset which is approximation of medial axis, and show that that subset approaches the medial axis. So I'm going to go through this really quickly and first review the definition of that stable subset of medial axis, which is due to Chazelle and Luiter in 2005. So what they do is they define a feature function of the medial axis, defined as, so I'm going to use a picture to explain. So for this little dot on the medial axis, you take the smallest ball containing the two nearest boundary points. The radius of that ball is called the feature of that red dot. And then given a constant, let's say lambda, you take the set of all medial axis points whose feature is greater than lambda, or greater or equal to lambda, and they give it a name called lambda medial axis. And this particular subset is stable when you perturb the boundary using Hausdorff distance that are very small. That small distance is related to lambda. So we can define something similar on the voxel core. So in our case, the feature size is essentially the radius of the smallest ball containing the boundary vertices to a face of the voxel core. And then given a lambda value, our lambda voxel core is essentially the set of all faces whose feature size is greater than or equal to the lambda. So it's exactly the same definition, we just changed how we define feature size. All right, and with this in mind, now present the main theoretical results of the paper. So we have to put some assumptions, and as in all sampling-based methods, we assume that the shape is smooth. So that means it's bounded by a C2 continuous surface, and our voxel size has to be small enough, and that enough is relative to what's called the local feature size of the shape. So when you satisfy these conditions, then we can show that first, the voxel core preserves the topology of the shape. And what's even more important is that the lambda subset of voxel core converges onto the lambda medial axis as your voxel size goes to 0. So when you increase the resolution of voxel size, we get closer and closer and closer to that subset of the medial axis. I would like to point out that the second property holds for any choice of lambda greater than 0. As you decrease lambda, you actually get approximation to a larger and larger subset of medial axis. And eventually, you're going to be able to almost approach the entire medial axis if you choose a very small lambda. The downside is that a smaller lambda means a slower convergence, so you have to use a finer voxel grid. So the lambda, as usual, gives you a trade-off between computational cost and your approximation quality. All right, so let's recap the algorithm. Given input shape, for example, a triangular mesh, you first voxelize it on a sufficiently high voxel grid, and then you compute the voxel core by computing the Voronoi diagram and stripping away everything outside the voxelization. And we use TETGen for voxelization. Sorry, for generating the Voronoi diagram. Now you notice that the voxel core is very complex. It does preserve the right topology, but it just has too much stuff. And that's why we had the third step of pruning using the lambda value here. So you compute the feature size of the faces, which is colored in the middle in the heat color, and you take away all the faces whose feature size is lower than lambda. Now, we have to be careful here to make sure the result preserves the right topology, so we did a topology preserving pruning from the voxel core, the complex one, to the lambda vox core, which is a small one. And that way we guarantee the result has the right topology. Okay, so let's see how it compares with existing methods. So again, we take Amenta-Kalouris method, which is one of the best methods so far with theoretical guarantee. So both our method and their method has theoretical guarantee that topology is correct as soon as your sampling is dense enough. But only our method can actually deliver that promise in practice here. I want to point out that the two medial axes are actually quite similar, visually very similar, as you see in the zoom-up view, which is kind of interesting because we take our samples on voxel grids, and you would think that the medial axis would look blocky, but it actually turns out to be quite close because as you increase the voxel resolution, you will get closer and closer to the two medial axes. And both methods take similar amount of time and memory. Here's one more example. In this case, again, their method generated over 100 topologic artifacts. And in this particular case, we generate even finer medial axis, as you see in the zooming views down there, but at the cost of slightly increased time and memory. Okay, so some more examples at even higher resolution. I would like to point out that none of the existing voxel-based methods, so remember voxel-based methods taking voxelization and strip away voxels, none of them can work at this resolution. They either crash or exhaust the system memory before they can finish because their complexity is just, they have to use all the voxels inside, where we only use the voxels on the outside. So we're able to process data at high resolution. And I would like to present a final example, and this is really a motivation of work. It's a part of a collaboration with a bunch of biologists who are interested in the shape of plant roots. Unfortunately, their data size is just too big for any of the voxel-based algorithms to extract medial axis. So this is a corn root created, imaged by high-resolution X-ray imaging. And this is a medial axis that we created. Now, to give you a sense of why this is useful, we can now plug in the medial axis to one of these curved skeleton algorithms and generate curved representations of the roots. And then we can measure shapes of the roots, for example, the length of the roots, where each root is, and the branching pattern using the curved skeleton. And this is an ongoing project right now. So to summarize, we present yet another sampling-based algorithm for computing medial axis with improved numerical stability and also simpler. Some limitations for future work. The first one, as you probably observe really closely, is that we can have some alias and artifacts on our medial axis. And that's natural because we use samples on the grid. So it would be nice to kind of smooth them out, for example, using a post-process deformation. And even though we can process larger volumes than existing methods, we still have trouble processing huge volumes. So nowadays it's quite common for CT scanners to come out with volumes with 4,000 cubed or even higher, and we're going to have to use a humongous machine to process those volumes. So the question is, can we do even better? Can we be even more efficient than being linear to the number of boundary voxels? So one promising idea there is using octree adaptive grids. And finally, extension to higher dimension is always interesting. And the last thing I want to show is that we present the program and the code online on GitHub. And in fact, you can find two projects in there. One is this project presenting today, computing medial axis from any shape. And the other one is the one that presented in SIGGRAPH 2 years ago that takes medial axis and compute a curved skeleton or surface skeleton. And in fact, this current project grew out of the frustration in that project that we don't have good medial axis to start with. So I'm glad that we have a good solution now. So I would encourage you to try them out. And thank you.
We have 2 minutes for questions.
So you mentioned that you still have to make the assumption that your shapes are C2, but the technique employs this voxelization, which is not C2 and is not even C1. So is there some prospect of extending this to cases where the shape is not in any way smooth?
So first of all, right, the voxel shape is C0. But we require C2 so that you can guarantee that your voxelization capture the topology of the shape. Right now, the best result so far in terms of voxelization and topology is that, it's limited to C2 shapes. Because the voxel size is a fraction of the local feature size of the shape, and the local feature size can go to 0 if you have a sharp corner, right? If it's smooth, then the local feature size is positive, then you can guarantee that voxelization has the right topology. I just came back from a conference in Canada, a computational geometry conference, and there were some interesting results there on showing that you can actually voxelize in 2D polygon shapes that preserve its topology. So it'll be interesting to see that line of research extending to 3D to provide similar guarantees on shapes that are not smooth.
Okay, and then I have a second question, which is, can you talk a little bit more about the topology preserving pruning?
Yes, so this is a part that I intentionally skipped because it's a simple process. You take a complex and you remove faces of the complex while preserving topology, and there is a standard procedure for doing that, and it's quite a simple process. Essentially, you remove two elements with alternating dimensions at the same time, and that way you can preserve the homotopy of the shape. Yes.